Okay, today we've got congruence transformations in store for us. Lesson 4.7. So here's some of the things we're going to be doing. We're going to be looking at reflections, translations, rotations. And those are all under the umbrella of transformations. It means we're moving an object around, okay? We're not changing it. It is still the same object. It has not been, nothing's been done to the object except that it's been moved, okay? It's not been shrunk, it's not been enlarged, it's not been skewed in any way, okay? So, they've got a lot of good information on this very first page, page 296. They've got an information about what a transformation is. It's an operation that maps an original geometric figure, the pre-image, onto a new figure called the image. A transformation can change the position, size, shape of a figure. Now, today we're not changing the size or shape. We're doing what's called rigid transformations, and you may hear that on a standardized test where they say a rigid transformations happen. That means what's only happened to it is a reflection, a translation, or a rotation. It doesn't mean it's been dilated, which that means it's been enlarged or reduced. And so right now we're only talking about rigid transformations. And they mentioned that word that I just talked about right here, rigid transformation. Another word for rigid transformation is isometry. And again, it's one in which the position of the image may differ from that of the pre-image, but the two figures remain congruent. So we're going to focus on verifying, like when things have been switched around, are the figures still congruent or not? So here at the bottom, they've got an example of a reflection, a translation, and a rotation. A reflection right here, kind of think of this arrow or line here as like a mirror. And so it's like a reflection of each other. So think of it in that way when you're trying to figure out like which angle is congruent to which angle. Think of it as a reflection like from the mirror, okay? Perspective. A translation, which is next, is simply just moving the object, over left or right or up or down or a combination of the two. You're not flipping it around, you're not reflecting it, it's just simply picking it up and moving it right or left, up or down, and it could be a combination of moving it up and to the right or to the left and down. It can be a combination of things. Rotation, you're actually rotating it, okay? A rotation or turn is a transformation around a fixed point called the center of rotation through a specific angle and in a specific direction. Each point of the original figure and its image are the same distance from the center, okay? So they're just showing you how a rotation occurs. So we're just going to hit the ground running and just identify in each one of these what could be happening. So we're going to work with 1 through 4 here first. And if you look at number 1, I hope you notice that we've got 2 diamonds, and I will tell you some people have different perspectives of what can happen, and sometimes there can be more than one right answer. But from here, what this one looks like to me is that if you just kind of pick this point like right here, okay, and then I'm comparing it to this point over here because it looks like they're the same orientation. It's not a reflection because they're not straight across from each other anymore. The green one's up a little higher, and you wonder, well, how much higher? Well, if I just picked a reference point, the far right, okay, point of each of these figures, and I noticed that going from the blue to the green, it's been moved up to the x-axis, right? And so, let me try and make this a little, so it's been moved up, you can see right here, right? And then also you'll notice that this line has been also moved over. That point has been moved over that much and up that much. I don't know if that helps you see that this little point, I'm going to erase this right here because I like how I did this second. So basically you can see that this point moved over and up, okay? And then you can look at each one of these. This one down here did the same thing. It moved over and up. This one over here moved over and up, over and up. And so you can kind of, like I said, you just pick a few points and you can kind of see consistently that they moved over, and I'm going to erase all this now and just focus on one. But if you did this for all of them, you would notice that they moved over approximately 1, 2, 3, 4, 5, and up a half, okay? Moved over and then up about a half, okay? So that's a translation. Type of transformation. Then we look over here, and this one, I hope you can clearly see that going from the blue to the green, it's not moved up or down, but it looks like it's moved over, but you'll notice that it's flipped over. And whenever I think the word flipped, I think reflection. So think of this as your mirror, this little red line, and that is a reflection in that mirror, so to speak. And also you can think of reflection, it's perfectly symmetric. Like this point here is exactly the same distance from this red line as this point is over here, okay? Or if you pick this point is exactly the same distance from this line as that point straight across from it. It's very symmetric, okay? So just keep that in mind. So that one's a good example of a reflection. Then we're going down to some real life pictures that you might actually see. And I'm going to let you guess right there which one you think that is. Okay, hopefully you said reflection, because if you notice, basically the top, okay, is reflected over this horizontal, I'm going to call it X line, and it's a reflection. And if you were looking at this picture, you'd probably say, oh, look at it's reflecting in the water, you know, be really cool. Okay, and then you think of a Ferris wheel. It rotates around this point right here, right? So it might start here, but then it's going to rotate around, and that person will eventually be like right over there, right? So that would be a rotation. All right, let's move on over to 6, because I'm going to let you do 5 on your own, because 5's easier. The reason it's easier is because you can, I'm going to give you a little hint so that it will be easier for you. You can actually count like how long XY is by just counting, because it's perfectly vertical. And then you can also, the counting will give you that length. You won't have to use distance formula. And likewise, from Y to Z, you can just count because it's perfectly horizontal, and the only one you're going to have to find the length of is this side right here and this side right here, okay? Those angled sides you are going to have to find the length, but you could do that with distance formula or Pythagorean theorem. And again, over here on this green triangle, you can just count and count, okay? So they want you, basically what they're wanting you to do is verify that it is what type of transformation it is, and then confirm that they didn't alter the triangle at all when they did that transformation, that it is the same length. It has 3 congruent sides, which is legal, because remember we learned about side, side, side. If we have 2 triangles, and all the sides are congruent to the sides of the other triangle, then those triangles are congruent to each other. So that's what you're doing. So you can count 2 of the sides on both of those triangles. You're only going to have to figure out the length of the slanted, or in this case, the hypotenuses, okay? So you could, just to clean this up, to find these, you can, like I said, you can figure out this length. And now keep in mind that the x-axis is in 2s, okay? But the, and also the y-axis is in 2. So just kind of keep that in mind when you're counting, all right? So I'll let you handle that. And then over here, not so easy, because I don't have any that I can just count, okay? All of them are slanted. So what I'm going to have to do is the distance formula over and over again, okay? And it looks like on number 6 that to me it looks like a translation, because just looking, if I compare like the M, it went over a certain amount and then down a certain amount. So and then if I look over here, I'll probably realize that this one, let's see, started here and then went down. And you'll see, like, if I drew that accurately, that it should be translated exactly, and I just want to make sure that the sides are the same lengths, okay? So how I'm going to do that, I'm going to do distance formula. So let me erase this stuff. What I'm going to do is I'm going to, for time's sake, I'm going to do a few of these, the distance formula, okay? And I'm going to state it there, and then you just need to finish it out. But here's the distance formula. Now, if you like doing Pythagorean theorem, you can do that, okay? I don't know what the choice is of most students, but this one would be really easy to do Pythagorean theorem, because it is already drawn, okay? So, but let me look more specifically. The only reason I would be against Pythagorean theorem is just this one's a little bit harder to count, but really shouldn't be that difficult. And you can go ahead and assume that if it's not right on the cross an integer, that it's at half, okay? So let's just look at MP. So I'm going to see if MP is congruent to JH. So I'm going to show you an example. It's always good to mark your coordinates. So this one is, P is at -9 and 2. And then M is at -4 and it's up at 7. Okay, so I'm just going to show you how you do this. So we're going to plug that back in here. Now I'm going to call this x1, y1, okay, and this one x2, y2, just to keep stuff straight. So I'm going to subtract my y, or no, I've got x listed first. So I'm going to subtract my x2 and x1. So I got a -4. Let me write this out. I don't want to do it too much in my head and confuse you. Plus, it's more likely to make mistakes. All right, so x2 is -4 minus -9. And then, let me make sure that's clear. Minus -9. There we go. And then my y is 2 is 7, okay, and my y1 is 2, so 7 minus 2 is going to go over here, squared. Then you just have to be real careful with your math, negative 4 minus negative 9 is actually negative 4 plus 9. So that'd be 5 squared plus 5 squared. So that's going to be a square root of 50. All right, so that tells me that this segment PM, and actually I probably should have wrote that at the beginning, PM. Okay, so I can keep track. So PM is the square root of 50, and I'll just rewrite it down here so we know exactly what we did. Okay, so now I'm going to confirm that JH is also the square root of 50. So again, I'm going to go down to JH, and now I'm going to get those coordinates down. So H is at negative 1 and negative 5. Let's see, negative 1, negative 5. Okay, and then J is at 4, 0. This is going to be a little bit easier because, and make sure your negatives are clear because that can be a problem. So I'm going to call this x1, y1, and this x2, y2. Okay, so I'm going to do the same formula again. I'm not going to rewrite it though. I'm going to use this formula. I'm going to subtract my x's, I'm going to subtract my y's, and then square them. So I'm subtracting my x's, and I'm doing x2, and I happen to identify it. My x2's up there is 4. So 4 minus a negative 1 squared, and then my y2 was 0. And then my y1 was negative 5, so it's 0 minus a negative 5. All right, so when I do this, I'm going to get 4 minus a negative 1 is 5, so I got 5 squared. And then 0 minus negative 5 is 5, so 5 squared again. And you'll notice this ends up being square root of 50. And that is side, let's see, PM was the, so HJ. So here I've just confirmed that indeed, as I suspected, these two sides are congruent. Okay? And so I would do the same thing for these two sides and then these two sides. So basically you would do the distance formula 4 more times. Okay? And I'll put in red what you should get. So they told me SM is supposed to be square root of 45. JK ends up being square root of 45. And PS ends up being square root of 65. And then HK ends up being square root of 65. So after you've done, like I said, 4 times and gotten those numbers, we can confirm that it is congruent. We can say triangle JHK is congruent to triangle MPS. Why? Because of side, side, side. This shows up here that all 3 sides have congruent sides on both triangles with a corresponding congruent side on the other triangle. So they are congruent in length, okay? So, and as I said, we didn't write it here, but this one was square root of 50, and this one was square root of 50. And so we've just proven that they have pairs of congruent sides, 3 pairs, in fact, okay? And so that's kind of how you do it. Like I said, your number 5, you're only going to have to do the distance formula once for each triangle, and you're going to confirm that these hypotenuses are congruent to each other by doing this distance formula right there, okay? So you'll do it for XZ and LJ, okay, just like I had to do over here, a pair. And then the others you'll just count, and you'll be able to count how the lengths, how long they are, and to figure out if they're congruent or not. Okay. Now, let's see. Let's move on to see if I need to give you any other additional information. Oh, I do want to go over one like number, let's see, the ones I'm going to have you do. I want to go over number 9 with you, because it is a little bit different, okay, than what we've talked about. Oh, the directions say, identify the type of congruence transformation shown as reflection, translation, or rotation. I just want to let you know that you could have more than one right answer. Okay, it's just, you have to pick one. It's not all, it's not like all three have happened. You just pick one. So I want you to look at number 9 and think, do you think it's reflection, translation, or rotation, and why? Okay. Well, actually, any of those answers are correct. You could have put translation, reflection, or rotation. Here's why. Let's pick the first one I mentioned, translation. So let me just pick a point. Let me pick this one. Let's see where I can get it in the same screen. Let me pick this top one right here, okay? And then this top one over here. So if you compare those two, you'll realize it went up and then over a certain amount. And then if you pick this one, you'll realize, oh, it went up and over the same amount also, okay? And so if you went around, you realize, hey, it just went up or over. So you could say translation just from that, okay? Just picking each one of these points, and you can physically see the shape is the same. They've not altered the shape or anything, and you can just see they've just kind of picked up the blue-looking star and placed it up and over, up 4 and over 4, it looks like. 3, 4, 1, 2, 3, yeah. And I'll kind of clean this up, and you can clearly see when I said up 4, see it went up 4 and over 4 to get to that point. So every one of these tips of the star, you could say that happened, okay? So now let's see if you thought reflection, okay? So if you thought reflection, that could be equally correct, because it's a different way of looking at it. We've not really looked at it from diagonal, like over the origin, but there is a reflection line, like right, let's see if I can draw this accurately. There is a reflection line right there. It's drawn diagonal. Normally we're used to it being vertically up or horizontal, but actually it's reflected across that line to kind of pretend your mirror is right there, okay? And so that could be a reflection. And then it could also be rotation, because oh, didn't mean for it to do that. I was trying to erase this right here. Okay, it could also be reflection, or I just said reflection because it's like over a diagonal line. And the last one is rotation. That one might be a little bit harder to see, but if you were just to rotate this around over here, around the origin, and just flip it, like if you were to put a pin on the origin and just rotate it, like if this was on paper and you stick your pencil through it and just rotate it, you could get it to the star to be over here in the from the third quadrant over to the first quadrant, so to speak. So it could be rotation, and it's rotated around the origin right there. So that one was kind of interesting. It could be you can name any of those and be right, okay? So when you're doing those types, be looking at that. Now I want to look at any other, I'm just going to browse right now for myself. Any others I want to go over? 15. I think the rest you can get. Now 17, I want to give you a hint on that one. They give you coordinates for triangle, okay? So when you look at 17, let me get down there. Oh, I don't have it on my list here. All right, so let me just write it in. So 17, if you look on in your book with me, it gives you 3 coordinates, okay? They give you M, they give you P's, and they give you R's. And they give you another set of coordinates, T, V, and S, okay? And so they give you coordinates, and it says -7, -1, okay? For M, and for P, it's -7, -7, and R is -1, -4. So what I would do, and then you've got your 3 others, okay? So what you want to do is just take some graph paper and graph these. Excuse me. Okay, so there's your M, and then your P is going to be at -7, -7. 1, 2, 3, 4, 5, 6. Please do this on graph paper. It'll just be a lot easier because I can already tell that these are lining right up underneath each other because their x-coordinate's the same. M and P both have a -7 for their x-coordinate. So I already know I'm just going to be able to count this length of this triangle from here, and on graph paper it's going to line up perfectly, and you'll see that. And then -1, -4, so that would probably be right there, and that's going to be R. So there's your first triangle, right? So as you can see, you can just count from here to get that length, and then you're going to have to use the distance formula for these sides to see. And then you'll do the same thing with your T, V, and S. Okay, you'll graph those, and then you're just going to do like we did in numbers 6 and 5, where you'll use the distance formula to figure out if the other sides that are kind of at a slant position are congruent or not. But like I said, you'll just need to graph those on graph paper, and then once you do that, it'll be exactly like numbers 5 and 6 that we already did. Okay? Hope that's helpful, and you're going to get some great practice using the distance formula for sure. All right, until next time.